Hi everyone, I'm here to introduce my course project of robot learning at Cornell University. The title is TADM, Transformer-Based Any-Step Dynamics Model. Model-based reinforcement learning is a subclass of reinforcement learning where the agent constructs an internal model of the environment's dynamics and uses it to simulate future states, predict the rewards, and optimize actions efficiently. In model-based RL, the most important concept is dynamics model, also called world model due to the famous paper world models. As shown in the figure on the right, as an analogy to human intelligence, we expect the world model can imagine what will happen after the boy hits the baseball, with which we can optimize our policy based on the imaginations. To propose high-fidelity world models, many efforts has been devoted by previous researchers. Although their algorithms greatly improve the model precision in shorter rollouts, it is still challenging to predict the transition dynamics in long-horizon rollouts due to the inevitable bootstrapping prediction. But as proposed in the paper shown in the caption of the image below, the authors proposed a new method to reduce the compounding errors caused by the continuous bootstrapping predictions of the future states. By backstrapping to case k belongs to 1 to m earlier state, or we call the anchor state, where the m is the maximum length of backstrapping, the algorithm Any-Step Dynamics Model, or called ADM, can achieve lower errors when performing long-horizon rollouts, as shown in the figure above. Experiment results also show that the larger M can bring more accurate rollouts. However, according to the experiment results provided by the original paper, larger m such as m equals to 10 cannot ensure a better performance. We then hypothesized that the problem is due to the inherent problem of recurrent neural networks. As shown in the figure on the left, the author employed a GRU as the encoder to encode the state action sequence. When the m is large, although the GRU has reset gate, it is still possible that the last hidden layer output will lose some information from the previous state action pairs, so which then further cause the prediction errors. Then we realized that the transformers has proven their ability in sequence modeling tasks, and using transformers to replace the recurrent neural network structures in the reinforcement learning tasks has captured researchers focused in recent years, such as transstreamer model shown here, where the main improvement is to use attention mechanism to replace the temporal processing framework of the recurrent neural networks. Then we combined the features from ADM and TSSM. We proposed a new framework, transformer-based any-step dynamics model we call it TADM, where we keep any-step prediction feature of ADM and the attention-based sequence modeling of TSSM to ensure the performance of the world models on long-horizon rollouts with larger M. We hypothesized that by using attention mechanism, we can reduce the Lipschitz constant of the one-step prediction error bound with respect to the state through shorter information passed from the anchor state st-1 to +1 to st. We test our results on classic gym environment Hopper v5, where we have 11-dimensional state and 3-dimensional action. The plot on the right side is the performance provided by the author of the ADM paper. We aim to achieve better performance on the same task. Here are some parameters we adopted during the experiments. Due to the computational and time limit, we reduced the dimensions of the actor and the critic networks of softer actor-critic structure, and the dimensions of the hidden layers of the recurrent neural network, and the TADM is also reduced to 64. Every agent collects 50K real environment steps, with a longer backstrapping length m equals to 10. Where the performance degrades possibly due to the recurrent neural network structure. As shown in the test video here, although they have not achieved the convergent performance of soft actor credit due to the reduced network structures, The TADM achieved the best performance within the 50K environmental steps. We also experimented the GRU structure with only one attention layer. The performance is also improved. For takeaways, first, according to the figure here, using transformer encoder to replace the recurring neural network structures in model-based RL tasks can really reduce the number of steps to achieve certain rewards. Secondly, as shown here, this method can also reduce the errors of the world model's prediction on the unseen transitions, which further helps the agents to optimize their policies. Thanks for watching.